Somewhere in a quiet galaxy, 20 million light years from your bedroom, a star 25 times heavier than our sun simply disappeared. Not exploded, not cracked apart, not thrown its skin into space. It blinked out the way a match goes out when you pinch the flame. One moment it was the brightest red beacon in that part of the sky. The next moment it was gone, and in its place, the astronomers who watched it found nothing they had ever been taught to expect. If the same thing happened to our sun right now, you would not see it coming. You would not feel the heat fade. You would not hear a warning. You would only notice, somewhere between one heartbeat and the next, that the sky outside your window had gone the wrong color. And by the time you looked up to ask what was happening, the question would already be over. The light would not have left. It would not be on its way. It would simply not exist. There would be no wave for it to ride. The line between the sun and your eyes would be severed in a single instant. That did not happen to our sun. That did happen to a star whose name most people will never know. And the more carefully scientists looked at what happened to it, the more they realized that everything we thought we understood about how a giant star dies might be wrong. Not a little wrong. Not, we need to revise the numbers wrong. The kind of wrong that forces textbooks to be rewritten. The kind of wrong that turns old certainties into new questions. The kind of wrong that makes the night sky feel, for a moment, like a place we have never actually visited. By the end of this video, you are going to meet that star. You're going to understand what it did, why no model in any textbook predicted it, why some physicists are quietly admitting the model may be incomplete, and why one missing star might mean we have been miscounting the deaths of the universe's largest stars for decades. You are going to learn that the universe does not always announce its endings. To understand what that star did, you have to first understand what every astronomer believed a giant star is supposed to do. Imagine a candle, a thick birthday candle, almost as wide as your thumb. You light it, and the flame is steady, yellow, warm. The wax melts at the base, climbs up the wick, feeds the flame, and burns. As long as fuel keeps arriving, the flame keeps going. As long as fuel keeps arriving, the light keeps coming. Now imagine that the candle is the size of a city, then the size of a country, then the size of the orbit of the Earth, then the size of the orbit of Jupiter. Now imagine it is hotter than anything you have ever felt, hotter than the surface of the sun, hotter than a welding torch times 1,000, a sea of glowing gas the size of a small solar system, held together not by walls, but by its own weight, the gravity of the gas pulling every part of it inward, while the heat of the burning inside pushes every part of it outward. Two forces, balanced, a war that lasts millions of years. That is a massive star, and the war is the entire point. Inside the core of a massive star, the temperature and pressure are so high that atoms are crushed together. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, oxygen becomes silicon, silicon becomes iron. Each step takes more heat, more pressure, more courage from gravity to hold the furnace shut. Stars are, in this sense, slow machines for building up the periodic table, one element at a time. Every atom of calcium in your bones was cooked inside a star. Every atom of oxygen you are breathing right now was cooked inside a star. Every heavy element on Earth, from the salt on your table to the gold in wedding rings, was forged in the deep belly of a star that lived and died before the sun was born. And the moment iron appears in the core, everything changes. Because iron is special. Iron is the element at the center of the periodic table, at the boundary between atoms that release energy when they fuse and atoms that absorb energy when they fuse. Up to iron, fusion gives off energy. From iron onward, fusion costs energy. It does not pay back. So once the core has built up enough iron, the furnace has nothing left to burn. The heat supply cuts off in an instant. The outward push from the fire disappears, and the inward pull from gravity wins. The core collapses. It falls inward at nearly a quarter of the speed of light. The atoms crush together. Electrons merge with protons, becoming neutrons. A solid ball of neutrons the size of a city appears at the center of what used to be a star the size of a small solar system. The outer layers of the star, falling inward, slam into that neutron ball and bounce back. A shockwave races outward. The star tears itself open from the inside. A supernova. The most violent explosion a single object can produce in a single moment. For a few weeks, it can outshine an entire galaxy of 100 billion stars. That is the textbook story. That is what every university teaches. That is what every astronomy show has repeated, with variations, for 60 years. A massive star lives, burns, and ends in a fire so enormous the word fire feels too small for it. But here's the thing. For the last 15 years, astronomers have been quietly counting the dead. Not the supernovae themselves, but the stars that should have become supernovae. And the numbers do not match. The math is straightforward. We know how many massive stars form each year in a galaxy. We know how long they live. We know what fraction of them are big enough to explode. Multiply those numbers by the number of years a galaxy has been around. and we know how many supernovae it should have produced. Then we count the supernovae we have actually seen: the Hubble Space Telescope, the Chandra X-ray Observatory, the Lick Observatory Supernova Search, the Pan-STARRS Survey, the Catalina Sky Survey, and dozens of other teams have been carefully cataloging these explosions for decades. By about 2015, the discrepancy became too big to ignore. We should be seeing far more supernovae than we are seeing. Not a small difference. A large fraction of the most massive stars are somehow ending their lives without producing an explosion bright enough for us to catch. And the obvious question became impossible to ignore: where have the missing supernovae gone? Two possibilities presented themselves. Either astronomers are wrong about how often massive stars form between about 18 and 40 times the mass of the Sun, or massive stars sometimes die in a way that produces no bright explosion at all. That second possibility sounded like science fiction. And yet, when computer models were run, including the leading stellar evolution codes from groups in the United States, Japan, and Europe, the answer said yes, it might be possible. If the core of a massive star collapses in a very specific way, if the outer layers of the star fall inward along with the core instead of getting flung outward by a shock wave, then the entire star simply sinks into its own gravity well. No big explosion, just a quiet closing. Everything the star was slides into the black hole it becomes. No flash, no bang, just a soft click of the cosmic door. This idea was first suggested on paper more than 20 years ago. At first, it was considered an edge case, a curiosity, maybe one star in 100. Then more calculations were done, and more. And by the middle of the 2010s, the models kept saying the same thing. A non-trivial fraction of massive stars, maybe 20%, maybe more, should be failing to explode. They should be disappearing. Astronomers had a prediction. They did not have a witness. And then, in early 2009, a star in a galaxy called NGC 6946 did something quietly strange. NGC 6946 is a galaxy about 20 million light-years from Earth, in the direction of the constellation Cepheus. It sits on the edge of the sky most casual stargazers never look at. It looks like an ordinary spiral galaxy turning slowly in the dark. It has become famous, however, for one particular reason. It has produced more supernovae than almost any other galaxy we have ever cataloged. 9 in the last 100 years. Some of them were discovered by amateurs, sitting in their backyards, scanning the sky with backyard telescopes and posting their findings to internet forums. The galaxy earned a nickname. Astronomers call it the Fireworks Galaxy. In 2007, a team at Ohio State University started a long survey of the Fireworks Galaxy, watching dozens of its most luminous stars, hoping to catch a supernova as it began. They used the Large Binocular Telescope on Mount Graham in Arizona, the Hubble Space Telescope, and the Spitzer Space Telescope. They took pictures. They took spectra. They took more pictures. They took more spectra. They tracked the brightness of each star over time, looking for any sign of unusual behavior. One of the stars on their list was cataloged as NGC 6946 BH1. It was a red supergiant, a bloated, cool, luminous star of about 25 solar masses. It sat near a spiral arm in the Fireworks Galaxy. It shone brightly in the infrared. It was one of the brightest single stars in that galaxy. In 2007, BH1 began to brighten, slowly at first, then more strongly. By 2009, it had brightened by a factor of about a million times the brightness of our sun, briefly, all pouring out from a star that was approaching the end of its life. To astronomers watching, this looked like the start of a supernova. The textbook pattern matched: a brightening, a precursor, then the expected explosion. The textbook explosion did not come. Instead, over the next few years, BH1 began to dim, slowly at first, then faster, then dramatically. Year by year, it faded. By 2015, the bright red star was simply gone from the optical sky, gone from the visible light surveys, gone from the ultraviolet surveys. The place where it had shone for millions of years was empty. Something else was still there, a faint infrared source. The Spitzer Space Telescope picked it up, a low, fading glow. The glow was exactly what astronomers expected to see if the outer layers of the star had fallen back onto the black hole that had just formed inside it. The star had died. It had become something else, and it had done so without the supernova. Adams, the lead scientist of the survey, called it the failed supernova. The star had simply gone away, quietly, without a sound, without a torch, just the slow fade of a candle that has lost its wick. For a long time, even after the result was published, many astronomers refused to accept it. They said the team might have mismeasured the distance. They said the object might be hidden behind dust. They said the team might have subtracted the background wrong. They said the faint infrared glow might be something else entirely. Every objection was checked. Every counter-hypothesis was examined. Other teams reanalyzed the data. In the end, the result held. N6946 BH1 had failed to become a supernova. It had done the thing that theoretical models said should happen, but had never seen before. It had vanished. Then, in early 2026, a second event hit the headlines. This time, it was closer. This time, it was in the Andromeda Galaxy, our nearest large galactic neighbor, only about 2.5 million light years away. A team at Columbia University reported in the journal Science that they had watched a massive star in Andromeda, cataloged M31 2014 DS1, quietly disappear without producing a supernova. The star had brightened slightly, then dimmed, and then was gone. Just like BH1 almost exactly. A second quiet death. 2 confirmed cases, 2 missing explosions, 2 stars that textbooks said should have lit up like city blocks, but instead just stepped into the dark. And this is where the story turns from interesting to revolutionary. Because if 2 of these events have been confirmed in a region of space where astronomers can see in detail, then the math is no longer a curiosity. It is a reckoning. Astronomers estimate that somewhere between 10 and 30% of massive stars may end this way. Not in fire, in silence. That means for every 3 supernovae we see, there may be 1 star that vanished without a whisper. And there may be many more we have missed entirely. The implications are enormous. First, the universe may be hiding the births of black holes. Every black hole we have ever confirmed was made by either a supernova, a neutron-star merger, or a direct collapse of gas in the early universe. If massive stars can quietly become black holes without supernovae, then black hole formation is more common than we thought. There could be many more black holes in the universe today than the supernova counts would suggest. Black holes hiding in galaxies we have looked at, behind stars we cataloged, drifting in orbits we never noticed. Second, the brightest stars and galaxies may be quietly disappearing. When a red supergiant, 25 times the mass of the Sun, collapses and disappears, the galaxy it was in does not only lose a future supernova, it loses a beacon. Red supergiants are among the brightest individual stars we can detect in distant galaxies. They are used as distance indicators. They are used to map the spiral arms. They are used to estimate the ages of stellar populations. If a fraction of these beacons are quietly turning off, our maps are incomplete. Our distance ladders have invisible gaps. Our pictures of distant galaxies are missing some of their brightest landmarks. Third, the periodic table may still be complete, but the process by which it was built may be different from what we thought. The heaviest elements on Earth, the ones heavier than iron, are thought to form either in supernova, in neutron-star mergers, or in some combination of both. If some massive stars do not explode, then they do not contribute their heavy elements in the way the models assumed. That means the relative abundances of heavy elements in the universe may be subtly different from what we calculated. Not by much, but by enough to matter if you are trying to figure out where the gold in your wedding ring came from. If the geological record on Earth says that gold arrived in a certain way, but the astrophysical inventory says only so much gold could have been made by the supernovae we counted, then part of the missing gold has to have a missing explanation. Fourth, the chemistry of distant nebulae may be telling a story we have not yet read. When astronomers analyze the gases inside the giant glowing clouds in galaxies, they read them like fingerprints. They measure how much oxygen there is, how much carbon, how much iron. They compare those ratios to the expected yield of supernovae and quiet collapses. If the ratios do not match the visible supernova record, then the quiet failures have to be a real contributor. They have to be out there, brewing elements without being seen. And this is where the night sky gets a little more honest. Because the truth is, we have never actually counted every star that has ever died in a single galaxy. We have never actually watched a real-time galactic census of massive star deaths. We have only counted the deaths that announce themselves, the loud deaths, the fire and smoke deaths. We have been biased toward the bright, the dramatic, the obvious. The quiet deaths, the silent disappearances have been invisible to us. And the night sky is full of things that disappear in silence. Stars can dim slowly without ever exploding. Stars can be swallowed by companions. Stars can drift behind dust clouds that grow thick enough to block even their brightest light. Stars can have their surfaces eaten by a partner. Stars can hide in the glare of larger stars nearby. The list of ways a star can vanish without dying is long. The list of ways a star can die without telling us is longer. And sometimes the absence of a star is the loudest signal we have. To understand just how strange this is, compare the missing supernova to something closer to home. Imagine you live in a small town. Every year, a few houses burn down. The fire department keeps track of each fire. They check them off a list. After 50 years, they go back and ask, how many houses burned? The number they wrote down matches what the firefighters saw. So far, so good. Now imagine that, all along, a fraction of houses had been quietly demolished at night. No fire, no siren, just a vacant lot where a house once stood. The fire department has no record of these houses. They were never on the fire log, but the lots are empty. And if you go and count the houses that should still be standing, Based on how many were built, the number is short, quietly short, by a meaningful fraction. That is roughly what has happened in the universe. Astronomers are the fire department. Supernovae are the fires. And there are missing houses. And the missing houses matter. Because a star turning into a black hole without a supernova has a future. It becomes part of the galactic archive of dark objects. And those dark objects have a way of growing, of merging, of becoming the seeds of bigger black holes, of influencing the orbits of nearby stars, of bending space-time in subtle ways we have not yet fully mapped. The more missing houses there are, the more dark mass there is in galaxies, scattered in ways we did not expect. Some of that dark mass may already be influencing the motion of nearby stars, in patterns we have been quietly attributing to dark matter without ever considering that some of it might be ordinary black holes made by quiet deaths. This is the part most people do not want to think about. Because if even a fraction of what we previously called dark matter is, in fact, ordinary black holes created by these silent deaths, then a part of one of the great mysteries of modern cosmology is just possibly a little less mysterious, and no one wants to be the one to say it out loud before the evidence is solid. But it sits there in the back of the room, whispering, and it whispers to anything that is willing to listen. Now, here's the part that breaks the spine of the whole story, because even if the failed supernova is real, even if we now accept that some massive stars quietly collapse into black holes, the models say the resulting black hole should not be light. When a star 25 times the mass of the sun collapses in silence, with the outer layers all falling back in, the black hole it produces should weigh in at about 5 to 10 solar masses. That is consistent with the black holes we see in X-ray binaries. That is consistent with the black holes we detect via gravitational wave events from merging pairs. That is normal. That is expected. But in 2024, the James Webb Space Telescope began looking at the faint infrared glow that remained after the collapse of BH1. The Hubble had given us a rough picture, JWST gave us a sharper one, and the infrared emission suggested the black hole might not have pulled in all the outer layers. Some material from the outer envelope might have escaped, drifting outward in a slow, cold plume. The plume glowed faintly in the infrared. The shape was irregular, and the color suggested it was colder than any supernova remnant JWST had ever catalogued. What this means is that the failed supernova is not a clean disappearance. It is a messy one. The star does not simply wink out. It leaves a faint cloud, a fading afterimage, a residue. The black hole at the center is surrounded by the ghostly clothing of the star that used to be. This has consequences for how astronomers search for these events. They cannot just look for a star that has gone missing. They have to learn to look for a small, dim, slow, fading infrared blob where a star used to be. And they have to learn to see it against the bright background of an active galaxy, which means JWST and its successors are going to spend the next decade hunting these ghostly afterimages. And if they find many of them, the recalibration of cosmic inventories will be enormous. More questions will follow. If the failed supernova leaves behind a faint infrared cloud, how long does that cloud take to fade away completely? A few thousand years? A few million? If it is on the longer end, then older failed supernovae may be hiding in our own galaxy in the form of dim dust clouds near regions where astronomers once saw bright stars. And this is where things get really weird. Because if a failed supernova leaves behind an infrared glow that can last for millions of years, then some of the dim, dusty nebulae we have catalogued without explanation may themselves be the fossil record of massive stars that died without an explosion, tiny graveyards of stillborn black holes, the great extinctions of the stellar world, written not in fire but in cobwebs of warm dust. Every time we look at the sky with a new instrument, we change the story. We do not add to the story. We do not refine the story. We rewrite it. Now connect all of this to something larger. The story of stellar death is the story of cosmic recycling. Stars are born, they burn, they die. The materials they made are spread into space. New stars are born from those materials. Planets form around those stars. Life, if it gets a chance, builds itself from the cooked leftovers of long dead stars. Every atom of carbon in your body, every atom of calcium in your bones, every atom of iron in your blood was made inside a star that exploded. Supernovae are, in a real sense, the furnaces that built us. If a star fails to explode, where do its atoms go? Many of them fall into the new black hole. They vanish. They are removed from circulation. They cannot become newborn planets. They cannot become new chemistry. They cannot become life. In a universe where many massive stars die silently, a larger fraction of the cooked elements are locked away inside black holes, never to be released. Cosmetic chemistry for the universe becomes a closed ledger. Some of the raw material for new stars, new worlds, and new living things is missing. Not missing from the universe overall, because the universe is huge and the loss per failure is small in proportion, but missing in a quiet, accumulating way, like a slow leak in a swimming pool. You do not see the water dropping until one morning the pool is half empty. This is one possible answer to one of the great, quiet puzzles of cosmology. Why is there so much ordinary matter in the universe that we cannot see? Why is there, on average, less heavy element mass in galaxies than the supernovae we have counted would suggest? Why does the chemical inventory of the cosmic web feel a little understocked? Maybe, just maybe, some of that missing matter went quietly into the floor of black holes, born in silence, locked away without a sound. The universe does not always announce its endings. There's a part of this story that is philosophical, and it is worth sitting with. We humans love the loud endings. We write poems about supernovae, not about quiet disappearances. We illustrate stars exploding, not stars fading. Our cultural idea of cosmic drama is about violence and brightness. We have not yet built a cultural idea of cosmic silence, and yet the silence may be more common than the noise. The whole universe may be running on a different rhythm than the one we have been dancing to. And here's where I want to leave you with something that does not fit on a poster, but is worth holding on to. Most of what we know about the universe, we know because something shouted. A supernova shouted, a flare shouted, a collision shouted, a pulsar screamed. The biggest discoveries of the last century have been, almost without exception, loud. The telescope makers, the surveyors, the spectroscopists, all found what they found by chasing noise. The next great discoveries may be quiet. They may be the absence of something where something should have been. They may be a dim star we expect to see that is not there. They may be an infrared cloud that should not be there. They may be a slightly wrong count, a slightly off ratio, a slightly smaller inventory than the math demands. And if a generation of scientists grows up trained to look for absence rather than presence, trained to read the room for what should be there and is not, they may start seeing farther than we ever did. Because we have spent 200 years learning to listen for what the universe says, we have barely begun to listen for what it does not say. And what the universe does not say is sometimes older and stranger and more important than anything it has ever shouted. If this made you feel as small and unsettled as it made me feel while I was writing it, that feeling is the right one. Hold on to it. Carry it with you. Because the next time you look up at the night sky, you will see the same view everyone else sees. But you will know that somewhere in that same view, a star has just disappeared and no one else noticed. And that is the feeling of being alone with the cosmos. That is the feeling of carrying a secret that the sky has not yet decided to share. If that feeling reached you, subscribe, because the next videos in this series are going to go to even stranger places. We are going to talk about stars that should not exist, about galaxies that should not have time to be old, about black holes that grew up too fast, about a universe that does not stop surprising the people who spend their lives trying to know it. And we are going to lean into the silence, because the silence is where the next big thing lives. And while you are here, leave a comment. Tell me this. If one day a star quietly disappeared and astronomers could prove beyond any doubt that the universe was hiding massive stars by the billion, would you rather live in a louder universe where the biggest deaths announced themselves loudly, or in this quieter universe where the biggest deaths slipped into the dark? Because the answer you choose tells me what kind of universe you would prefer to believe in. Now look up. Tonight, the sky will look almost the same as it looked last night. The constellations will be the same. The Milky Way will still be a faint smear across the dark. And you will remember, every time you look at it now, that somewhere in that same faint smear, a star is going quietly missing right now, faster than you can blink, without telling anyone, without a sound. The universe is louder than we are, and the universe is quieter than we are. Both are true, and both are worth living with. The universe does not always announce its endings. That is not cruelty. That is grace. The grace of a cosmos, older than the oldest story, choosing every once in a while to step back into the dark without a performance, without an audience, without a single spotlight. And we are the ones left, alone in the dark, watching the place where it used to be, holding the bigger question. How much of what we think we know is only what has been loud enough to be heard?